All right, so for our next colligative property, we'll start off with this question. You guys might not know this, but in colder areas, right, why do we salt roads when it's cold? So in colder areas, before it snows, they'll go drive around and salt the roads. And the reason they do this is to melt the ice or keep the ice from forming in the first place. So next question is, why does this do this? Why does salt do this? And so that's our next colligative property, and this is called freezing point depression, right? So the opposite of boiling point, right? Depression means less. And so solutes will do two things. First of all, they're going to lower the boiling point, or the freezing point, the freezing point or the melting point, whichever way you want to think about it, and broaden it as well. Right, so solutes will lower and broaden the melting point / freezing point of solids. And so the equation here is essentially the same as the previous one. It's delta TF equals molal times KF, right? This delta TF is going to be the change in freezing point or melting point, whatever you want to call it. It's the same thing. This is molality. And then this is KF. This is just a constant that you would look up on a table. So let's just go ahead and do a real quick example of this. So the question here is you have 1.5 molal solution of water. What's the freezing point, right? And so we use our delta TF equals molal KF. We find water over here, and then we find our KF, not the KB, if I use the KF. And then molal, we know this is 1.5, so we just go ahead, plug these numbers in, right? 1.5 times 1.86. We'll get a 2.79 degrees Celsius. Does that mean water freezes at 2.79 degrees Celsius? No. Remember, this is just the change in the freezing point, not the actual freezing point. So if we wanted to find the actual freezing point, we would take the freezing point of the pure stuff, and now we're going to subtract the delta F of the freezing point, right? And again, the reason we subtract is because it's called boiling point depression. It will lower the freezing point. So you just got to kind of know that, right? So we got to subtract because we need to get a lower number at the end. So we'll take this 2.79, plug that into there, take our original freezing point of water, which is up here at 0 degrees Celsius. And so the freezing point will be 0 minus 2.79 degrees Celsius. And so the freezing point ends up being negative 2.79 degrees Celsius as our new freezing point. So the fact that solutes lower and broaden the melting or freezing point can be used to determine the purity of compounds. So oftentimes in Gen Chem labs, we'll do melting point tests, right? If we have what we think is maybe pure, pure compound A, and we know the melting point of pure compound A, we'll do a melting point test, and how close it is to the real value, that tells us that it's pure. The closer it is, the more pure it is. The further it is from its normal freezing point, the less pure the compound is. Finally, this is just kind of a little picture. So this is our phase diagram, right, from before. You should recognize this. But now you see we kind of have this range, right? And so this range kind of explains the difference between a pure compound and a solution of the same compound. So just know freezing point depression, boiling point elevation.